So today we will begin analysis on the transient portion for capacitors and inductors. So chapter 4, right? Chapter 4. And let's see. 1, section 1, and chapter 4. Okay, there you go. All right, so transient analysis deals with the portion of charging or discharging of the energy storage devices before and after, before and after steady state. Okay, so steady state, of course, refers to the state of a capacitor or inductor where the voltage or the current does not change with respect to time. If these components are completely discharged, meaning they do not have any stored energy, their voltage or current is not changing with respect to time. So it is technically a steady state, right? Now, when you apply a DC voltage or current to a capacitor or inductor, it'll start receiving the energy. And once it starts receiving the energy, that energy transfer takes some finite amount of time, right? The energy that is being received in the capacitor or inductor requires a finite amount of time, and we call that phase the charging phase. And then when the energy is released back into the circuit, it again takes the same finite amount of time. This time is dependent on the circuit parameters, meaning the component values for the capacitor, the resistor, and the other components in the circuit. And of course, on the applied energy. Now, when it reaches the full charge, we say that it has reached another steady state because once it's fully charged, the voltage or the current does not change, right? So far, we have looked at circuits that comprise of one inductor, one capacitor. In this chapter, our primary focus will be on circuits that comprise of only one capacitor and one inductor, okay? Similar to the previous chapter 3. When I say one capacitor or one inductor, it also means that if you have multiple components in a circuit, and if you are able to reduce it to one single capacitance or one single inductance, then technically we would still say that it is one single capacitor or one single inductor. Okay, so this one energy storage element or one element is not just physical. If the circuit is reducible, so it also refers to a circuit where you can reduce it to one single capacitor or one single inductor. Okay. So when energy is transferred into the components, we say that the components are being charged or charged up. When the components release the energy back into the circuit, we say they are discharging. Okay, they're discharging. And between the two steady states where they are charging and discharging, the voltage and current values change with respect to time. So our analysis basically requires deriving a equation that describes the voltage and current. And that, in short, is basically transient analysis. Okay, so the analysis of circuit during the energy transfer phase is known as transient analysis. Now, unlike resistors, we have seen in chapter 3 that capacitor voltage and current, or capacitor and inductor voltage and current, are time dependent, right? Capacitor current I is C dV over dt, meaning derivative of the voltage. Similarly for the inductor. So the voltages and currents are time dependent. So we are now involved with derivatives and integrals. And so analysis of these circuits require the solution of a first order differential equation. Okay, first order differential equation. Now, I don't know about you, but solving differential equations is not at the top of my list of fun things to do. All right. So again, derivation is not important. Well, it's important, but what I want students to focus on is basically understanding the process, how to actually apply the techniques that you have learned, and then we will have a general purpose equation that you can use. Okay, so it requires the solution of a first order differential equation, and hence it is known as a first order circuit. Okay, it is known as a first order circuit. And the reason is because if it has one energy storage element, it requires a first order differential equation. If you have two energy storage elements, it requires solution of a second order differential equation. And then we call that circuit as a second order circuit. Okay, second order circuit. So one energy storage element is a first order circuit. Two requires a second order differential equation, and so it's known as a second order circuit. All right. Now, typically the circuits are referred to as RL or RC. Okay, there's always a resistor in the circuit. So if you have an inductor and a resistor, we call it a RL circuit. If there is a capacitor and a resistor, we say it's a RC circuit. When you have two energy storage elements, they could be two inductors or two capacitors, and it may not be possible to reduce them. You would still have a second order differential equation. But for the most part, when we study these circuits, a second order circuit is typically one that contains a inductor and a capacitor. So we call it a RLC circuit, second order circuit. Now, our primary focus is going to be on first order circuits. Second order, I will introduce the topic a bit, but we will not go, too in depth into those. All right. All right. Any questions? The basics make sense, right? Okay. So the transient response is the same for both inductors as well as capacitors. If we look at this graph right here, this one shows voltage, this one is for current. Now we can solve for voltage and current for both capacitor and inductor, but it's easier to write a voltage equation for a capacitor. So when it's a capacitor, we write the equation in terms of voltage. When it's an inductor, we write the equation in terms of the current. And I will show, we'll look at derivations for both. So as you can see here, we have time t equal to 0 right here on the x and y axis, right? We always have time on the x-axis. So at time t equal to 0 or before time t equal to 0, we can see that the voltage and the currents have a constant value. So we can define this region as steady state. Okay, we can define that region as steady state because the voltage and current is not changing with respect to time. And it begins charging. This is the charging phase. Same thing here, charging phase, where the voltage and current at any given point in time has a very different value. And this response is fleeting, right? Again, this is the energy transfer phase. That energy transfer can take place in a matter of microseconds. Sometimes it could take minutes. Just depends on the size of your component and also the amount of energy that you're transferring in there. Think of it as a bucket of water that you're trying to fill up, right? The smaller the container, the faster it's going to fill up. And the larger the flow, meaning the larger the energy storage, excuse me, the larger the energy source, the faster it's going to fill up. So again, there are quite a few variables involved in there, but the primary ones are basically the size of the container and the amount of energy that you want to transfer. Okay. Okay. So transient responses are of two kinds. We say there are natural response and there's a forced response. Forced is not as sinister as the word sounds. Um, all of the analysis that we have done so far can technically be classified as a forced response. Okay, forced response is basically something that is not inherently a part of the component itself, meaning there's an external source that is providing the energy, and that creates voltages and currents to appear in that component, which is basically everything that we have studied so far. Chapters 1, 2, and 3, we have a voltage source or a current source connected to a resistor or a capacitor or an inductor, right? And then these resistors, capacitors, and inductors will have some voltages and currents. So these voltages and currents do not come or do not occur automatically in these components. They are in response to an external stimulation like a source, like an external source. And hence it is known as a forced response. The other word to describe it is also a step response. A step response. Suffice to say, forced response is basically charging, and natural response is basically discharging, meaning there is no external source in there. Right? Remember, when you have a capacitor and inductor, you connect a source to it, it'll keep receiving the energy. The moment the source is taken away, all of that energy is going to be released back into the circuit. So when it starts releasing, the voltage and the current that appear in that capacitor or inductor does not require any external source. And hence, it is just discharging everything that is just naturally stored inside that component, and hence natural response. Okay. So to summarize it, forced response is charging, natural response is discharging. Okay. Any questions so far? We all good? Okay. So natural response circuits, the simplest circuit possible. Basically, you have a component, inductor or capacitor, and you connect it across the resistor. And all of the energy that is present in those inductors or capacitors is now slowly released into that resistor. And the resistor dissipates the energy as heat. So natural response circuit is basically a inductor and a resistor, RL. And on the right, you have RC. Note that the notations refer to EQ. EQ, so subscript EQ, and it has significance. Basically, there could be multiple inductors, multiple resistors in the circuit, multiple capacitors, and multiple resistors, but it is possible to reduce all of them down to one single inductance or one single capacitance. And the same thing with the resistance. So these are still first order circuits. The CEQ, LEQ, or REQ could be hundreds of capacitors in series or parallel. So physically, you could have more than one, right? Physically, you could have more than one. But schematically, if it is possible to reduce it down to one single equivalent component, then it is still a first order circuit. Okay, so the EQ, which stands for equivalent, one single component schematically. Oh. But physically could be hundreds of components. And you would still have a RL and RC circuit. Okay. Does that make sense to everyone? So it would be your job to take a problem or a circuit and realize what kind of circuit it is, whether it is possible to reduce it down to one single component. And if it is, then you can apply these standard equations. Similarly, for the step response circuits, we take the exact same circuit, meaning you have R and L, and you insert a source in there, right? So you had R and L connected together, and you simply inserted a source. Same thing with the capacitor. We inserted a source to that capacitor and inductor. I mean, capacitor and resistor circuit. So this is RL. This is RC. And we have representation for both, right? We can solve it for voltage. We can solve it for current. If we are trying to solve for voltage, we would have a Thevenin equivalent circuit connected to that capacitor. If we are trying to solve for current, we would have a Norton equivalent circuit connected to those components. So this is the Thevenin equivalent. This is the Norton. And the reason would become clearer as we go along. But the reason we would want to have Thevenin or Norton is if you have a source and the source is connected to a capacitor, but there are several resistors in the middle. There are several resistors before it gets to the capacitor, then we need to determine the exact voltage that is being applied to that capacitor. Or similarly, if you have an inductor, we need to find out the exact current that is being applied to that inductor. And that's why we need a Thevenin or a Norton equivalent circuit. Okay. Now, the Thevenin and Norton equivalent circuits are not going to be very complex or complicated for for these kind of problems. All right, any questions? Any questions at all? Okay. So let's look at the first circuit, RL, natural response. We have a circuit, we are saying we have a current source IS. Now, the current direction, the references, the polarity, they're there for, for convenience purposes, for explanations, okay? So don't get too bogged down into how and why the circuit looks, but let's understand the process. So we have a switch here. Think back to chapter 1 when I said you would have an arrow either pointing down or going up. So when it's going up, it tells you, and if there's a reference which says t equal to 0, it tells you that switch will open at t equal to 0. Okay, yes. Well, what happens after the switch is open? Good question. So if there's a source, why is it a natural response? So the thing is, most of these problems involve analyzing circuits where you have multiple, like let's say you have a square wave going in, for instance. So to model that kind of input signal, we use a switch, right? So when we have a switch, the circuit changes. So when the switch was closed prior to time t equal to 0, the source was connected. So prior to time t equal to 0, the source was like this. Now, most of these problems will always tell you, you have to analyze the circuit after the switch is either flipped open or flipped close at time t equal to 0, meaning that is the beginning point of our analysis. Okay, so t equal to 0 indicates the start or the beginning point of analysis. Okay, and at t equal to 0, when the switch is opened, the source and resistor R0 get disconnected. The only thing left in the circuit is L and R on the right, and the circuit becomes like this. And that's why it's a natural response problem. Right? So before time t equal to 0, the current source was connected. The inductor gets fully charged. Once it's fully charged, inductor acts like a short. Right? And once it acts like a short, everything's going to pass through that inductor. Nothing goes through anywhere else once you have a short circuit. Let's see, it's 9:58. I got a couple of minutes. So everything's going to the inductor, and at t equal to 0, when you flip the switch open, circuit reduces to this. Now, the only thing left in the circuit is the resistor R on the right. So all of the current in that inductor is now being discharged through that resistor on the right. And we want to write our equation. Well, we need to figure out what the initial energy is in that inductor. The initial energy in that inductor would be equal to that current source IS, because the inductor was being charged from that current source IS. Okay, current source IS. Let's see. Yeah. Got a minute left. I just want to talk about this concept right here. 0 plus and 0 minus. This simply means the time right after, and this is the time right before. Okay, so 0 plus and 0 minus simply indicate the time right before 0 and the time right after 0. This will be a very important concept for this entire chapter. And the reason it's important is because the current through an inductor cannot change instantaneously, and the voltage across a capacitor cannot change instantaneously. Okay, keep in mind these concepts, and we'll pick up here again on Wednesday. Okay, so review these concepts, and we'll pick up here on Wednesday. I have office hours today. I'll be available. If you do need to see me over Zoom, you send me an email. Sorry if I haven't made that clear. I need to send. I'll send an email and clarify. So please do not just log on to Zoom and wait around. If you need to see me on Zoom, send me an email.